Welcome back to Mechanical Engineering Made Simple.
We are really diving deep today. We're pushing past, the basic single degree of freedom stuff.
Yeah, moving into more complex territory.
Exactly. Our sources point to two really critical areas for real-world design.
Okay, what are they?
First, how we model structures where the mass and stiffness aren't just points, but are spread out continuously. Think beams, plates.
Like bridges, airplane wings, that sort of thing.
Precisely. And second, how these structures react to really sudden, sharp impacts or loads, things that aren't smooth or repeating. We call that the transient response.
Got it. So our mission today really is to equip you, the listener, with the core ideas and the tools engineers use for these advanced vibration problems. We want you to grasp why we need these methods for complex, real-world scenarios.
Right. It's about understanding how engineers actually analyze and, importantly, stop things from shaking dangerously.
If you've ever wondered how a skyscraper is designed to handle wind gusts, or how a car chassis absorbs a sudden bump, well, this deep dive gets into the thinking behind those calculations.
Okay, so let's start with the foundation. We need to talk about the difference between our standard models and, well, reality.
You mean lumped versus distributed systems?
Exactly. In basic mechanics, we often use lumped parameter systems. We pretend the structure is simple, like rigid blocks connected by perfect, massless springs and dampers.
It's an idealization, right? An approximation.
A very useful one. It gives us a finite number of degrees of freedom, or DOF, makes the math manageable.
But the real world isn't made of massless springs.
Definitely not. In reality, take any beam or plate. Its mass and its elasticity, its stiffness are distributed all the way through it, continuously.
So less like weights on a string, more like a metal ruler that flexes.
That's a good way to put it. And that continuous distribution, that's where things get, mathematically speaking, much more involved. A distributed parameter system fundamentally has an infinite number of ways it can move, an infinite number of degrees of freedom.
Infinite. Okay, that sounds complicated. What's the big consequence of that?
The really profound outcome is that these real systems have an infinite number of natural frequencies.
Whoa, infinite frequencies. How can you possibly design for that? Doesn't that mean resonance is always a risk?
It sounds like a nightmare, I know. But you don't track all infinite frequencies, you focus. For every single one of those natural frequencies, the structure has a specific way it likes to vibrate, a particular shape. We call that the normal mode or natural mode.
Can you give us a quick picture of a mode shape?
Sure. Think of a simple beam, maybe supported at both ends, like with hinges.
Okay.
Its lowest natural frequency, the fundamental one, makes the beam bend up and down in a smooth curve, like a single half sine wave.
Just one big arc.
Exactly. The next frequency up might look like a full sine wave, bending up in one half and down in the other, with a point in the middle staying still. That's the second mode. And it goes on, getting more complex.
Okay, I see. So infinite modes, infinite frequencies. But solving the full math, the partial differential equations, that sounds tough for real designs.
It often is very complex, sometimes impractical. So engineers lean heavily on approximation methods.
And if you just need that crucial first frequency, the fundamental one, what's the go-to method?
That would be Rayleigh's method. It's incredibly useful, really elegant, actually. It uses the conservation of energy principle for a system of vibrating freely without damping.
Ah, the energy balance trick. You're saying the maximum potential energy stored in the flex
The maximum elastic strain energy, yeah, when it's bent the most.
has to equal the maximum kinetic energy when it's moving fastest through the 0 point.
Precisely. You equate those two energy peaks, and the frequency just pops out of the equation. It's brilliant.
What's the catch?
The catch is you have to assume a shape for how the structure deflects, and your assumed shape needs to be reasonably close to the real first mode shape and meet the boundary conditions, like how it's supported.
So if your guess about the shape is way off, your frequency calculation could be off too. How do we get more accuracy or find those higher modes?
Right, that's where Ritz's method comes in. You can think of it as a more sophisticated, more flexible version of Rayleigh.
How is it more flexible?
With Ritz, instead of assuming one fixed shape, you assume a shape that's built from a combination of simpler shapes, maybe a series expansion. And this assumed shape includes some unknown parameters, some adjustment knobs, if you will.
The adjustment knobs.
Yeah.
Okay, so you can tweak the assumed shape.
Exactly. You use calculus, basically, to find the values for those parameters that make the calculated frequency as low as possible, a minimum value.
Why minimum?
Because mathematically, minimizing the frequency calculation with respect to those parameters pushes your assumed shape closer to the true mode shape. It gives a much better estimate for the fundamental frequency, and you can even use it to get pretty good estimates for the higher frequencies too. It's about making a smarter, adaptable guess.
Okay, that makes sense. So we figured out how to find these critical frequencies, even with infinite possibilities. Now let's talk about fixing problems. What if a machine's operating speed lines up perfectly with one of these natural frequencies? Big trouble, right?
Potentially catastrophic, yes. Resonance.
And what if you can't easily redesign the main structure, maybe add damping directly into it? Is there another way?
Absolutely. That's when we bring in auxiliary mass dampers. Sometimes they're just called damped absorbers.
So you bolt on a smaller system to help the big one.
Essentially, yes. The idea is if you can't damp the main system directly, you attach a small, carefully designed secondary system, usually just a mass, a spring, and a damper to soak up the vibration energy.
How does that actually work? How does this little attached thing calm down the big structure?
It's all about the force the auxiliary system exerts back onto the main structure. It pushes and pulls on the attachment point. Now, if there's no damping in the auxiliary system, that reaction force just kind of shifts the main system's natural frequencies around. It doesn't really kill the vibration.
Right.
But when you add damping to that auxiliary mass, something crucial happens. The reaction force it generates gets a component that is 90 degrees out of phase with the motion, the displacement, and acceleration of the main system at that point.
90 degrees. Why is that the magic number?
Because a force acting 90 degrees out of phase with velocity, or in this case displacement acceleration, which are also 90 degrees apart in harmonic motion, does work. It actively extracts energy from the main system over each cycle. It damps the vibration.
It's like applying brakes at just the right moments in the cycle.
That's a decent analogy, yes. It's actively fighting the motion by being out of sync in that specific way.
And designing these absorbers, I understand there's a clever trick involving fixed points on the response graph.
Yes. This is a really neat piece of theory. When you plot the amplitude of the main system versus the excitation frequency, for a system with a damped absorber attached, there are two special frequency points, usually called A and B.
And what's special about A and B?
At these specific frequencies, the amplitude of the main system's vibration is completely independent of how much damping you put in the auxiliary system. Whether you have a lot of damping or very little, the amplitude curve always passes through these same 2 points.
Wow, okay. Why is that so useful for design?
It decouples the problem. It means you can first choose the mass and spring of your absorber, which sets the tuning ratio, alpha, to place these fixed points, A and B strategically, usually aiming to make their heights equal. This optimizes the tuning without worrying about the damping value yet.
So you fix the tuning first, alpha Tachi, just based on these fixed points. That simplifies things a lot.
Immensely. Once you've got the optimal tuning set by the fixed points, then you choose the optimal amount of damping, zeta opt, to minimize the peaks of the response curve that occur between and around those fixed points.
Got it. Tune first using the fixed points, then optimize the damping. Are there other types of absorbers too?
Oh, yes. You can sometimes use distributed masses like long rods, but that's usually only practical at very high frequencies. A more common one, especially for rotating machinery, is the pendulum absorber. It uses the inertia of swinging pendulums to create torques that cancel out unwanted torsional vibrations in things like engine crankshafts.
Fascinating stuff. Okay, we've covered continuous systems and how to tame them. Let's switch gears completely. What about sudden shocks? Bangs, impacts, sudden starts or stops?
Right, now we're moving into transient response. We're looking at loads that aren't smooth and continuous, but act suddenly, maybe just for a short duration. Think a step input, like suddenly applying a constant force, or a pulse, like a brief blast or impact.
So the goal isn't finding a steady vibration amplitude anymore.
Exactly. Now the goal is to find the entire time history of how the system reacts to that sudden event. What's the peak displacement? How long does it vibrate afterwards?
One thing our sources really emphasize here is a kind of mathematical elegance, how different kinds of shocks can be described similarly.
That's a really powerful insight. Whether the shock comes from a force hitting the object, the VAC-TD, or the ground suddenly moving underneath it, YLTD, or even the ground suddenly accelerating.
Like in an earthquake.
Precisely. The actual differential equation describing the system's response, whether that response is absolute motion solidar, motion relative to the ground delta, or even absolute acceleration, can often be boiled down to the same general form, plus nu plus down.
So one equation structure covers all these different physical situations.
Essentially, yes. ONUA represents the response quantity you care about, and TEP represents the effective excitation based on the input. You solve the same type of equation, just plugging in the appropriate sellers for your specific shock.
That must save a lot of work.
It does. For instance, take a simple undamped system at rest. If you suddenly apply a constant force equivalent to a step input B6,
What?
the solution is 1 omega t. It doesn't just move to the position in stock.
It oscillates.
Yes, it oscillates around cyclets. And notice the cosine goes from +1 to -1, that term goes from 0 to 2.
Meaning it overshoots. It actually reaches twice the amplitude of the step input.
Exactly. The peak response is $2. That dynamic overshoot is critical in transient analysis.
Okay, so how do we actually find these time response functions, especially for more complex pulses?
There are two main classical workhorses here.
Which are?
First, there's Duhamel's integral, which is also called the convolution integral.
What's the idea behind Duhamel's?
It's quite intuitive, actually. It thinks of the complex input force as being made up of a whole sequence of tiny, infinitesimally short impulses.
Okay, it's like a series of tiny hammer taps.
Exactly. And we know how a simple system responds to a single impulse. Duhamel's integral just adds up or superimposes the responses to all those tiny individual impulses over time to get the total response to the complex input. It gives you a good physical feel for how the response builds up.
That makes sense. What's the other main method?
The other big one is using the Laplace transformation.
Laplace transforms. Very powerful math tool. What's the advantage here compared to Duhamel?
Laplace transforms excel at turning differential equations into algebraic equations. You transform the whole equation, including the forcing function, into the Beal's domain.
Making it easier to solve.
Usually, yes. But the key advantage, especially for transients, is that the initial conditions, the displacement and velocity the system had right at the start of the shock, get automatically incorporated into the algebraic equation in the S domain.
Oh, I see. Duhamel might be trickier if the system wasn't starting from rest.
It can be. Laplace handles initial conditions very cleanly. You solve the algebra, then transform back to the time domain to get your Mélange part. So maybe Duhamel for physical insight, Laplace for mathematical efficiency, especially with initial conditions.
Okay, so we get the full-time history, but engineers often need just one number, right? The worst-case scenario.
That's right. They're usually most interested in the absolute maximum response the system reaches during or after the pulse. That's called the maximax response, denoted amplec.
And how do they visualize that?
Using response spectra. A response spectrum is a plot. It shows how that maximax response ample top changes depending on the properties of the pulse in the system. Often it plots a ratio of the pulse duration to the system's natural period, tallow dollars. So
you can see how systems at different natural frequencies will react to the same pulse.
exactly. And these spectra reveal crucial patterns. For many common pulse shapes like rectangular or half-sine pulses, the biggest amplification, the highest ANO, usually happens when the pulse duration shout is somewhere around 0.5 to 1 times the natural period dollars.
So when towers between, say, 0.5 and 1.
Roughly, yes. And critically, that peak maximax response is often about 1.5 to 1.8 times the peak value of the input pulse itself. It's
Wait, so the dynamic effect amplifies the peak input load by 50% to 80%?
potentially, yes. That amplification factor is vital for safe design against impacts or blasts. You can't just design for the static peak load, you have to account for this dynamic overshoot.
That's a huge safety factor just from the dynamics. And for those step inputs, you mentioned the peak occurs after the input has reached its steady value.
Yes, for step-like inputs. The system is still accelerating when the input force levels off. Inertia carries it past the new equilibrium. That maximax response, 9 is actually the sum of the final steady displacement, plus the amplitude of the vibration after the step is complete, which we call the residual response amplitude, NER. So 1 error plus, it's still ringing.
Okay. One last point on transients. Damping. We said for the auxiliary mass dampers, damping was crucial. How important is damping for surviving a single short pulse?
That's a really important distinction. For steady-state vibration near resonance, even a tiny bit of damping makes a huge difference.
Right.
But for the maximax response to a single pulse or step, normal amounts of viscous damping often have relatively little effect on that first highest peak.
Why is that?
The shock happens too fast. The system reaches its peak displacement so quickly that the damper just doesn't have enough time or cycles to dissipate a significant amount of energy before that first peak occurs. You'd need very heavy damping for it to substantially reduce swing.
Interesting. So damping is key for fatigue life under continuous vibration, but less critical for surviving the peak load from a single shock, unless it's extremely high damping.
That's a good summary. It really highlights the different design philosophies for continuous versus transient loads.
This has been fascinating. We've gone from continuous beams to sudden shocks. It feels like the real challenge is putting it all together, right?
Absolutely. Think about a complex structure, like a whole airplane wing or a bridge deck, getting hit by a sudden gust or impact. That's a distributed system experiencing a transient load.
So you need both sets of tools we discussed.
Precisely. The advanced approach involves using the normal mode analysis, like we discussed with Rayleigh and Ritz, to break the complex distributed system down into a set of equivalent, independent, single degree of freedom systems.
Decoupling the complexity using the modes.
Exactly. And then you apply the transient analysis methods like Duhamel or Laplace to each of those independent modal equations to find out how each mode responds to the shock. Then you add those responses back up.
Wow, that's the real synthesis. Combining mode shapes with transient solutions. It sounds computationally intensive for complex structures.
It definitely can be. And for doing that kind of analysis efficiently, especially for systems with many, many degrees of freedom, engineers rely on more advanced computational techniques. Methods like the phase plane delta method or the transfer matrix method are designed specifically to handle that complexity for transient problems in multi-degree of freedom systems. That's where the heavy-duty computing comes in.
A glimpse into the next level of analysis. This has been incredibly insightful, bridging the gap between simple models and these really complex dynamic realities.
Until the next equation, we will see you design junkies on the next episode of Mechanical Engineering Made Simple.